So now the conditions are given. A always throw to B. This first condition. When B gets the ball, B always throw to C. Then when C gets the ball, he equally likely throw either A or C. Okay, he will throw to either A or B. Okay, so this is the condition. Now we have to show that the process is Markovian. Find the TPM, transition probability matrix. Classify the states. That means we have to classify whether the state is periodic or not, what is the behavior, all these things. Okay, so let us do this. Okay, now let us go for the matrix directly. Capital P. So three guys are playing. So I'm taking these three guys are A, B, and C. So you see A cannot throw the ball to A, B cannot throw to B, and C cannot throw to C. So this is one condition. Now we know that the guy A always throw the ball to B. That means probability cannot exceed more than 1. So he 100% will throw to B. So he will not throw to C. Similarly, B will throw the ball 100% to C. So the probability is 1 because it is sure evens. And B to A is 0. But now C can have a probability equally likely. He can throw to B or he can throw to A. That means 50-50% is their probability he can throw either to A or to B. So this forms the transition matrix. Now students see, to check ergodic all these things, we have to make a matrix irreducible. So for irreducible, as I said, Pij at any step should be greater than 0 for all I, j. Now you see already here 1, 2, 3, 4. 4 elements are already non-zero. Now what we have to do? We have to make the remaining 5 elements should be non-zero. It doesn't mean at the step. This is step 1. We can go for any number of steps. So as per the formula, P square is simply P into P. So now we are going to multiply this matrix. Okay, you can do your using calculator. So now you see 0. Already these two positions are, you don't bother about the next step. Okay, here this is 0. In the new step, P square, this become non-zero. Good. Here this also, this element, the remaining one become non-zero, and this one become non-zero and non-zero. So see, out of 9 elements, 4 elements are non-zero here, and in the second step, another 4 elements are non-zero. This only one guy is going to be 0. So let us proceed further. Let's go for P cube. So we can take P square P or P. So similarly, so now in P square, what happened? You get 1 by 2 here. So this is the only remaining element which is 0 in the first 2 steps. You see, both in the first 2 steps, this is the only element commonly becoming 0. Other elements from non-zero, it becomes non-zero. So now it is done. So 1 by 2, 0, 1 by 2, 1 by 2, 0, 1 by 4, 1 by 4, 1 by 2. So this is enough, true irreducible. But for the case of periodic or aperiodic, we will need a little more step. We'll go like P5 or P6 such that all the elements will become non-zero. Okay. So P cube into P, again if you evaluate, you will get 1 by 2, 1 by 2. This is just for our reference. Okay. Here itself, in the step 3 itself, all the elements become non-zero. Okay. Here, these are all for further reference we are doing. Similarly, P5 I will do, where most of the cases you see at P5 or P6, you will arrive. This, all the elements should be non-zero. That's it, students. You see, now all the elements are non-zero. Now let us go to the discussion of the problem. From this calculation, we say that all the elements are non-zero, right? In first step, this 4 is non-zero. In second step, the remaining 4 is non-zero. In third step, this guy is non-zero. That all Pij are non-zero for some I, j and n, right? That's it. So now, like what we can say here in particular, Pij 3, Pij 1, Pij 2. In this 3 steps itself, we found that everything is non-zero, right? In this 3 sets, Pij 1, Pij 2, Pij 3 itself, we found all the entries are non-zero. So now what we can say, this Markov, according to the theorem, if all the entries are non-zero at some step, then the Markov chain is irreducible. This may be asked as a MCQ student. When you say a transition probability matrix is irreducible, then you have to show all the entries are non-zero at some step. Okay. Now, what we know, if a Markov chain is irreducible, then we have a result. If it is irreducible and finite, okay, then all the states have same type of periods. Okay, that means if state 1 is periodic, all the states are periodic. If state 1 is aperiodic, you don't want to find the other steps. Okay, everything I have given in the material, very clear, you can verify. Okay, now we prove this is irreducible. Now let us take this. Any state we can take. You see, let us take this state B. Why I am interested on state B? Because first one is 0. Okay, at state 1 it is going to be 0. In the second state, you see the diagonal element non-zero. In this third state, non-zero. In the fourth state, non-zero. In the fifth state, non-zero. That means state B at step 1 it is 0. I cannot take the step 1. So step 1 it is, step 2 it is non-zero. So it is eligible for verifying GCD. In step 2, this is non-zero. So I put 2, that step. Step 3 it is non-zero. Step 4 it is non-zero. Step 5 it is non-zero. Is going on. Now what is the GCD of this? So this 2 and 3 are prime numbers. Obviously GCD is going to be 1. Okay. So now we can conclude GCD equal to 1. That means the state B is aperiodic. Okay. Aperiodic. So according to the result, if the Markov chain is irreducible and finite, it has same type of period. Because it is finite, reason is I have only 3 states, A, B, C. So this is going to be aperiodic. Therefore, what we can say, this Markov chain is, first of all, irreducible. First step. Second step, this is finite, obviously. Reason, it has only 3 states, A, B, C. Then third step, all states are aperiodic. If a state is aperiodic, then it is, okay, because we know the definition of ergodic. What is ergodic? A finite chain which is irreducible. We can say like ergodic, these 3 words you have to remember. Non-null, persistent and aperiodic. Then we can say it as ergodic. You see, this non-null and persistent by the theorem, if a Markov chain is irreducible, if you prove it is irreducible, automatically 2 conditions will hold. It will be non-null. Okay, non-null means non-zero elements. Non-null and persistent. So these 2 conditions can be accommodated if you prove it is irreducible. We have already proved it is irreducible. First one is done, non-null, persistent. Then finite, it is finite. And we proved this, all states are aperiodic. That means ergodic. Okay, is it clear, students?